Hello, we are Ucl Rover team and welcome to our Hypatia project. Affiliated with University College London, our team was formed in 2018 and the team has grown since. This year we are proud to present our new rover, Hypatia, for the 10th anniversary edition of the European Rover Challenge.
Our team is composed of several sub-teams with students from diverse backgrounds. The robotic arm team is focused on developing the articulated interface between the rover and the outside world. The base station team works on the rover's control hub, where our team orchestrates the rover's movement across the Mars yard, in addition to developing the autonomously flying drone using MATLAB Simulink. The science team studies landscape and terrain properties while developing the sample collection mechanisms for secure storage and accurate weighing. The mechanical team developed the backbone of our rover, focusing on the structural reliability, modular design philosophy, and subsystem interfaces. The autonomous and control team are the minds behind our rover's mobility, taking care in developing reliable path planning algorithms to negotiate difficult terrain and accomplish mission-critical activities with ease. Behind the scenes, the logistics team runs our operations, finance, and outreach, always looking for opportunities to grow the rover team. The European Rover Challenge is an incredible chance for us to work together across many fields. It challenges us to organize and integrate various subsystems, driven by our shared passion for space exploration and ambition to push boundaries. The fact that new challenges are introduced in the ERC every year, such as the redesigned Mars yard, keeps us on our toes and pushes us to innovate, making this a highly technical and demanding project. We are also motivated by the opportunity to collaborate and network with the other competing teams, connect with industry professionals, and listen to inspiring presentations by guest speakers from the space sector.
Section 1. Design Approach. We employ an iterative process in our designing and building, using the resources we have in MechSpace where we do our work. We consider how feasible our design is and even design our own testing strategies, such as a testing rig. Section 2. Rover Mobility.
To develop a functional 3D mapping algorithm, we utilize the fusion of spatial camera sensors such as Z and LiDAR to create a mesh of the surrounding environment using point cloud extraction methods. The Z camera uses depth and orientation sensors that facilitate object identification and detection. Its fusion with LiDAR provides a wide field of view for the rover.
To visualize the autonomous navigation of our rover, simulation software such as Gazebo and Arvis has been used alongside a simplified URDF model. The navigation of our rover is centered around making use of relevant ROS2 packages, such as the nav2 stack. Here we see the simplified rover model navigating between selected waypoints using a four-wheel drive system. After successful publishing of data from the depth camera and LiDAR sensor, SLAM techniques were implemented using the ROS2 SLAM toolbox. This provides us with a detailed cost map that would allow for efficient global and local path planning.
Section 3. Safety Systems. The Ucl Rover incorporates a comprehensive multi-layer safety system that integrates hardware, software, and procedural safeguards. Circuit breakers and fuses provide robust protection against electrical faults, complemented by an emergency stop button which ensures immediate cessation of all activities, stopping the rover within 1 second in emergencies. The software framework enhances safety through real-time sensor data acquisition for current, voltage, temperature, and power usage, facilitating active fault detection and response based on predefined thresholds. Additionally, procedural protocols include detailed pre-start checks and a sequence activation logic, ensuring that system operations commence without conflicts, with manual emergency intervention capabilities to immediately halt operations if needed. Section 4. Robotic Arm.
The robotic arm is an integral part of the rover, used in a variety of tasks across the competition. The maintenance task highlights the rover's functionality with a range of components, installed on a panel, and demonstrates adaptability and precision in manipulation across diverse terrain. To achieve this, the team has designed a robotic arm with 5 degrees of freedom, allowing for a large range of motion and comprehensive exploration and interaction with its environment. The rover exhibits real-time feedback, ensuring continuous monitoring and control, and maximizing efficiency and safety during operation. The science and probing tasks are accommodated by modular grippers that can be interchanged in a matter of minutes, enabling accurate and precise operation, and thus allowing different areas of the surface to be accessed quickly and easily, with current focus on developing seamless integration of autonomous and manual control modes. These tasks require exact and rapid sample and probe collection from the Mars yard surface to be deposited in our science cache.
Section 5. Science Cache.
The geology section aims to inform the construction and operation of our rover within a 100-kilometre radius. The subregion Noctis labyrinthus piqued a particular interest due to its checkerboard-style fracturing pattern. One of the origins of this may be due to extensive faulting. Another aspect of this region are pits, which may be formed by escaping groundwater from these faults, the layers of which can expose older geological material, which is particularly interesting for deep sampling. Using this geological research as a foundation, this is how we will adapt our rover to perform the science cache tasks.
To further narrow down a suitable sample region, the rover will also be able to obtain preliminary geological data, including humidity, temperature, and nitrogen content, through the deployment of a 7-in-1 soil sensor. The mechanism has been designed to actuate independently of the science cache assembly to allow for multiple deployments while reducing overall energy consumption.
Our compact deep sample collection system utilizes a drilling mechanism which is lowered by a double gantry system. An auger bit deposits the sample into our soil storage container. This features a load cell which provides real-time weight measurement accurate to 1 gram and a spectroscopy sensor to identify the specimen's organic nature. Designed for ease of access, the sample can be easily removed from the housing for further inspection and analysis back at the base station.
Section 6. Base Station.
In order to maintain communication between rover and base station, a transceiver has been chosen that uses a low 5 GHz frequency and has integrated omnidirectional antennas. Furthermore, to complete the drone tasks, the Reesteller drone was chosen. It obtains a lightweight nature and is accustomed to outdoor environment. MATLAB will be used to enhance the COTS low-level control to achieve a high degree of autonomous mode. This will ensure the drone's ability to accurately perform the necessary tasks of lifting off, taking videos of the angled markers, and emergency stopping at the designated location.
We are looking forward to showcase Project Hypatia, and thank you for listening.